Hi, I'm Brian Malow, and we are live from the 73rd Lindau Nobel Laureate meeting, and I am with one of the 630 young scientists here this year, Pratik Prasad Joshi. It's nice to talk. We've been talking all week, had some meals together, and so you are from India, but working in the United States. Not only working in the United States, but you are at the University of Illinois in Champaign, Urbana-Champaign, which just happens to be the school that my father went to. And that got us talking even more, right?
Yeah.
So, you're not a physicist, but you do work in a very physics-related field. You're really more of an electrical engineer.
Yes.
Electrical engineer. So, tell me, you're at, what department are you in at Urbana-Champaign?
I'm in electrical and computer engineering at University of Illinois Urbana-Champaign. That's what I got my PhD from. And as you might know, UIUC in short, it has a lot of heritage with Nobel laureates. Like the only Nobel laureate to get 2 Nobel Prizes in physics, John Bardeen, for invention of transistor and superconductivity, comes from EC, Illinois, is associated with that. There's Jack Kilby, who has gotten the Nobel Prize in 2000 for the integrated circuit. So there's a lot of rich history of inventions and fundamental discoveries, along with some companies like YouTube and Tesla, who have come from this great department. It's the top 5 engineering department in the United States.
And they let you in.
Yeah, I'm very grateful for the education.
And you're currently a postdoc, right? So you got your PhD, and you're not only a postdoc, but you're working on a really exciting NASA space mission.
Yes.
Tell me about it. What's the mission?
Yeah, so I'm the lead for retrieval algorithms for a NASA mission, which is being launched in next year. It's under the NASA's Heliophysics division, and it's called the Carruthers Geocorona Observatory. It's a discovery mission, which is going to observe the outermost region of a planet called the exosphere.
Of our planet,
of
the
our
outermost
planet.
region of Earth.
Of Earth.
And you just said a mouthful of things, because so before we get that, you said you're the lead algorithm scientist. What does that mean? So the algorithms are, how do you even would describe that? What are you working on?
So putting in a simple way, most space missions have 2 kind of algorithms which are required. One are the calibration algorithms and one are the retrieval algorithms. So the calibration algorithms is basically when a mission is launched, it goes on orbit. You have to have a frame of reference with respect to some static source in space. And you calibrate your instrument in space so you know what a number 10 in your measurement means, right? And then with respect to that reference point, then you can make meaningful measurements of your actual target. So that's called calibration algorithms. And then there's retrieval algorithms. So once you are observing the target, you should go from an observation, which could be an image of ultraviolet or infrared or visible, and then you convert it into actual scientific physical parameters, like it could be temperatures, densities, wind velocities, and so on. And then and that's the data which is released to public. So the retrieval algorithms go from observations to the actual scientific data.
So it's like the interpretation of this.
That's like
this stream of numbers. What does it all mean?
Yes, exactly. I mean, it's like how you convert what you observe into something which is useful, which is released to the public to do scientific discoveries.
Okay.
So those are the retrieval algorithms which I'm leading for this particular mission.
Okay.
Yeah.
And so the mission, the Carruthers Geocorona Observatory.
Yes.
So what is the Geocorona? I've always heard the word corona in terms of the sun. So we hear that when they're during a solar eclipse, the corona, the disk of the sun is blocked out, but the corona is that outer area, right? So the Earth has a corona?
Yes. So Earth, Mars, Venus, most of the planets in our solar system, and even the moons of planets all have atmospheres, right? and the outermost region of an atmosphere typically is called an exosphere, and that's what we call a corona, right? And because now this mission is about Earth's corona, so we call it geocorona, simple. And so this outermost region called exosphere is pretty much dominated by the lightest atoms, because as we go further and further, the gravitational field becomes smaller, right? So the only lightest atoms can be spread out. And that's atomic hydrogen. It's atomic number 1 in the periodic table. So that's why the main objective of this mission is to understand the atomic hydrogen density around the Earth, and and it spreads from 500 kilometers in altitude all the way to 60 Earth radii.
Yeah, let me go over a couple things you just said, because first of all, most people, when we think commonly about the Earth's atmosphere, that essentially we say, like, if a suborbital flight, if you've been to space, it means you've been about 80 or 100 miles up.
Yes.
Most of the Earth's atmosphere is within 100 miles.
Yes.
But by no means, but then it just gets thinner and thinner and thinner the farther you go, right?
Yeah, yeah.
And you said, and we discussed these calculations at dinner the other night, that you said that this exosphere extends, you just said 60 Earth radii, and the radius of the Earth is about 4,000 miles. Yeah. So we're talking about 240,000 miles, which is about the distance from the Earth to the Moon. So we're talking about the Earth's atmosphere extending beyond the Moon.
Beyond the Moon, yeah. It involves like the Moon. The Moon is going in and out. It's rotating, like has an orbit around the Earth, and Moon also has something atmosphere. So there's a Moon's exosphere, which is embedded. This is an extended set of planetary exospheres. And this region of space, right, because the hydrogen atom is so light, it has a very complex chemistry. And because it is extended so far, it's been very difficult to actually measure it or characterize it. And it's one of the very less known areas of space, which is very, very critical to two important questions, right? So one important question is, the loss of water from a planet, right? Because it's H2O, so hydrogen. So if a planet starts losing water, which is evaporating from the oceans and various sources like methane and so on, right? The hydrogen keeps escaping higher and higher, and it comes into the outermost region, which escaped to space forever. That's exactly what happened to Mars. So Mars became from an ocean-filled planet, now we know, to a very barren planet. And when will Earth become like Mars? That's one of the questions we want to answer.
Hopefully no time soon.
It's not anytime soon, that's what we expect.
But right now, we have a nice magnetic field that helps protect the atmosphere from being stripped away by the solar wind.
Yes,
right?
Yes, it does, yeah.
And I know that you said, but we'll come back to this mission, but we have in common that we each contributed, you probably more significantly, to another NASA mission that's about this very thing. Like, you're referring to Mars, and the Mars Maven mission, you did similar work on algorithms for it?
Yes. So while I was doing my PhD, I worked on the only 2 missions which did this kind of an hydrogen exospheric estimation. One was at Earth, called the NASA timed mission, and the second was NASA's Maven mission to Mars, very popular.
So you worked on the science in the planning stages, and then I did some work on outreach after it launched for outreach that would take place at science centers. So interesting coincidence. Yeah, I haven't, except for the people I worked with on Maven, I hadn't met anyone else that worked on it.
Yeah, it's an excellent team of scientists, brilliant people you'll find.
Yeah.
Maven team, time team, and those are the legacy missions. So the algorithms and the techniques I developed for those missions makes the background knowledge for a discovery mission like the Caruthers. Right?
So let's come back to the Caruthers mission, because you told me, well, first of all, something very interesting. You just hinted at it, which is that this exosphere that extends so far from the Earth, it's hard to observe because you can't observe it from low Earth orbit. You
Yes.
can't observe it from geostationary orbit, which is 22,000 miles high. So
Exactly.
where is the Carruthers Geo-Corona Observatory going?
Oh yes,
It
that's a very
launches
good
next year,
question.
right? Yeah. It launches next year, 2025.
Yes, it launches around this time next summer, 2025, an expected schedule launch. It's going to be, one interesting thing is, I'll mention, it's going to be one of the first ride-share missions by NASA, where it's going on a rocket, a SpaceX rocket, that's what it is, and it's going to have, there's two missions going to go launch on the same rocket, which is one is the IMAP, which is the Interplanetary Mapping and Acceleration Probe, NASA. And then there's this Carruthers Geo-Corona Observatory. And because the reason is because the mission is going to launch at a point called L1, Lagrange point 1, which is at an equilibrium. It is a point in space which has an equal and opposite gravitational field of Earth and Sun. So what happens is, it is a very stable location in space where you have a very less orbital drag, and it's much efficient for a long-term, mission and operations.
It's balanced between, because it's being pulled in one direction by the sun and another direction by the earth, and so it's a fairly stable place.
Fairly equilibrium point. And the advantage is that point is also about 240 Earth radii further down in space, so it gives us enough distance to image the entire extent of the geocorona which we want to observe. And that's basically a unique location, right, in a deep space that has never been done before, right? I mean, no mission to date has been dedicated to observing the hydrogen exosphere from this far vantage, and this is going to be the first discovery mission, as far as I'm aware, from NASA, which is going to image the entire exosphere in ultraviolet. Now you might want to know why ultraviolet.
Well, yeah, so here's like we didn't discuss, it's like, why are you studying the exosphere? What kind of what are you hoping to learn by studying this part of the atmosphere?
Yes, so one question is, like I said, the habitability of our planet when Earth become like Mars.
You know what? Let's walk a little away from that noise.
Sure,
It's not what I expected, but it's a little noise there. I'm going to leave my bag.
Okay.
And so I'm going to just ask you again. All of a sudden, construction noises. We don't need that. I don't mind the sound of ping pong, but let's just walk away a little bit.
Sure.
And see what we have here is a couple young scientists playing ping pong behind us. And So I'll just ask you again, why are we even interested in this exosphere? What are you hoping to learn from it?
One question is, like, at what rate is Earth losing its water? Its atmosphere is evaporating to space, and it's important for habitability. The second important question is that space weather, right? So basically, all the effects from sun, from stars, or galactic medium are affecting our satellites, right, through this hydrogen cloud. And until we understand it better, we will not be able to predict the time and magnitude of how solar storms or these effects affect these satellites. And then these satellites can damage our power grids. It can do radio communication, your GPS signal. You're pretty much, you will be, it has a very lot of implications for our economy, because if we lose our internet or satellites, right, we are pretty much at loss of economic losses, and there could be blackouts. So it's very important for the welfare of our society. At the same time, for our defense and national security, for our economy, as well as to know our place in space, like I said, habitability. So there are multiple big important reasons why this region has to be studied.
So it sounds very cool, and it sounds like you really love what you do. This is what I find, not everyone in life loves their job and is anxious to wake up in the morning and go to work. But I have found through the years, talking to so many scientists, you like your work, and you probably are excited to go to work because you're working on a NASA mission, right?
Yes.
So, but tell me in your words, like, what is it you love about what you do, about space, about science, about your job? What gets you excited to get to the computer and work?
Oh, it's just the thrill that I can discover something really new tomorrow. You know, I'm going to develop these algorithms, and I'm going to deal with a lot of data because it's a lot of observational work, and yeah, just the thrill of being able to discover something new. And the second thing is, if you create this new techniques, right, or new discoveries, and publish it in the field like space research, is going to be used for maybe decades, if not centuries. So you're creating some seminal contributions to the knowledge in this field, which will stay. It's not going to be obsolete like most maybe our everyday products might have. So it's a lot of satisfaction in impact, and we're working for the planet, right? It's the impact is the entire humanity. It's not just persons. So those are like points which really motivate me to just keep going and try. And what I will say, I was very curious about, you know, the nature, how the nature works, how the universe works, and that fuels me. Has fueled me since I was a child to really, you know, pursue, you know, physics and space.
So you've loved space for so long, isn't it? You may have dreamed of it, but isn't it hard to believe that you ended up working on NASA space missions?
Yeah, it's always been a dream. So I will say I come from a small city in India called Nasik in the state of Maharashtra, and my parents were physicists. My grandpa was my motivation as an astrophysicist, but there was no one in our family came to any higher education. I was the first one, and I was like, okay, I want to become an NASA scientist, and I want to go to the United States and make my way to there. And I'm very grateful for the teachers, to the great scientists I have met along the way.
Yes.
And we continue to in this Nobel Laureate meeting. And
thanks for providing a nice transition for us. That's so exciting. So yeah, right behind us is the Inselhalle, which is the main location of so many of the sessions for this 73rd Lindau Nobel Laureate meeting.
Yes.
And so tell me, what are some of your impressions? We've been here for a few days. Have you been enjoying it?
Oh yes, I've just loved it. I mean, so you know, one of the dreams also, I came to the US my dad always said me, if you want to thank me, you know, go find the fifth force in nature and win a Nobel Prize in physics. And
wow,
like,
it's what a low bar to satisfy your father.
Yeah.
just discover a new force of nature and I'll be happy.
And I think it's still a mystery. But yeah, I mean, that has been a big motivation for Nobel Prizes in general. I have followed the Nobel laureates for over 2 decades, and coming to or meeting Nobel laureates is one of the most profound experience a young scientist can have. And this is no lesser than a dream. I mean, other than winning a Nobel Prize yourself, this is the closest you can come to meeting Nobel laureates. And the best part of the meeting is that you can meet with these Nobel laureates in person. You can have meaningful discussions. You can ask them any questions. They advise you just like your teacher, an advisor would. You know, they give you ideas how to think. They share their experiences of life, how they transition from different fields, how they learned about different interdisciplinary concepts, their struggles, and they're just like, you know, you and me in so many of their journeys, and it gives you a lot of realistic and meaningful insights. There's an insights on the cutting edge problems in the world. What are the important problems to focus on in your career? That's one of the biggest, I think, takeaway, which we do not get in any normal educational programs easily.
Yeah.
So that's important. And then there's a lot of nice formats in this meeting. Like you get to meet other young scientists, some of the most accomplished people in their respective fields from all areas of physics in this case. But
And this year they're coming from 90 different countries.
oh my God, yeah,
Yeah.
that's like amazing. And people are so passionate in every single field. You just learn, you can get collaborations. You learn a lot of perspectives which we never thought about. Some of your own questions, get some meaningful directions, and you make lifetime networks and connections. Maybe 10 years down the line, you will be interacting with them in some career or different capacity you would never know. And some of your colleagues here might be future Nobel Prize winners, so you might get invited to a ceremony.
Yes.
So so it's just an outstanding and once in a lifetime kind of an experience, which I think is life-changing in many ways. And one last thing I would mention is they have a format called Open Exchange, where we have Nobel laureates, people from the industry, leaders, and the young scientists all participating in an open discussion on the current problems like quantum technologies, quantum science, quantum computing, quantum imaging, everything quantum. You have astrophysics, the next directions of space discoveries in astrophysics, the unanswered questions. You have biology, and what are the most meaningful intersections of physics and biology. And you have a lot of interdisciplinary themes which have been discussed, and in terms of it's a very open discussion. So there's no barriers to ask anything and everything you want. You get advice for how to write proposals, how to get funding opportunities as well. And then there are these really private sessions where a Nobel laureate just gives a presentation, and it's just a group of young scientists, and you get to learn from the best in the world, and at the same time you get to ask every question, and they are just some of the most humble and brilliant minds. I am just so grateful for every interaction. It feels like 24 hours or less.
Yeah.
I wish it goes longer and longer. So yeah, it's just
Well, Pratik, it's been really nice talking to you, and that's a really beautiful note to end on, I think.
Yeah. I would maybe like to add one message.
No! Okay, one more.
Yes, so for everyone from developing countries and developed countries, like I come from India, and also been studied most of my education has been the US. So I think I will encourage everyone to apply and talk to their institutions and the government to try to come to the Lindau Nobel Laureate meetings. It's an opportunity which is not very well known in every part. So please do come. And as an alumni, from next week onwards, I think we always be more than happy to associate and advise anything I can.
Yes, you'll be joining once this week. The meeting refers to you as a young scientist, but after Friday, you'll be part of the Lindau Alumni Network.
Yes.
And for people that are interested in learning more about the meeting and possibly attending, you can find out all this information on the website. But all around the world are partner academic organizations that are nominating organizations. And whether you're affiliated with one or not, on the Lindau Nobel website, Lindau Nobel Laureate meeting, you can find out more information about how you might be able to attend in the future.
Yes.
Like this guy. So nice talking to you.
Thank
And enjoy the rest of the meeting. There's still a couple days of amazing stuff.
Yes, and thank you so much, Brian, for this opportunity. And please win Nobel Prizes in the future, innovate and discover.